Take the last dance for me. Hey, it's Mr. K doing a video for AP Physics 1 and possibly C. This will fit for both. Here we have a simple harmonic oscillator. We got a mass on a spring. Let me turn my Michael Bublé down a little bit. We got a mass on a spring. It is a 5 kilogram mass on a spring, and this is all the information that we have. This right here, this graph. And if you look at the graph, it is a position versus time graph, and as you can see, this thing is moving somehow, some way. And this is going to be one where I want you to kind of work it out on your own for a little bit. Pause the video and see what all you can find. Of course, I did provide 2 more graphs over here, so that's kind of a hint as to what you might be able to do with this problem. But take a moment, however long you need, pause the video, and try to find out whatever you can find, and we'll see if what you find is the same thing as what I find. Okay? Alright, for those of you who paused the video and actually tried to work it on yourselves, awesome. Thank you for doing that. If you did not pause the video and you're just going straight to the answers, that's not really the point of this. So remember, in physics you got to practice the thing before you actually get it. But let's go ahead and start off, and we will see how we can approach this problem. First off, we have a position time graph, and what this thing is doing is going back and forth, back and forth, back and forth, back and forth. It's a mass on a spring. So if you imagine this object is a mass on a spring, much like the video that was right before this in the playlist, or if you would search for it, the simple harmonic oscillators kind of intro video. We have a mass on a spring that has been pulled to the right, and we let it go, and so it goes back to the left and goes like this, oscillates back and forth. If there was friction involved, you'd see this amplitude get smaller and smaller and smaller as time went on. So right now we have no friction, no other outside forces that we really need to care about except for the force of the spring on this mass. And so let's go ahead and try to analyze all that we can analyze from this graph. I'm not sure how much we can do. I just made this problem up, but let's go ahead and get at it. So first thing I can do is I can look at this and say, all right, I know that the amplitude of this thing is going to be this right here. That's how far away from equilibrium it would be. This is equilibrium. This is where it wants to be. Our amplitude is going to be 0.5 meters on either side of this thing. So it's actually rather large. It's probably up to your waist in height, depending on how tall you are. And so this thing is going back and forth, back and forth, back and forth. The amplitude's 0.5. We got that. So I'll just write that down on the side here. Amplitude, or the maximum x displacement, is about 0.5 either way, meters, plus or minus. That may come in and be important later on, may not. The other thing that we know is that this thing is moving. It's moving, and it's got some speed in the middle. It's got to turn around on the ends, right? So we got a velocity that's changing, and if we know what velocity is a change of position over a change of time. Or, if you're in calculus, it's a small, very small change of position over a very small change in time. And what that says to us is that, hey, that's the slope. So what's happening to the slope here? And what we can do to look at that is we can take a, let's see if I can find something that is rather flat. I'll take this. There we go. So if we look at this, we can say, oh, the slope here is going and it's changing as time goes on. And as that time goes on and we try to follow it and go like this, our slope is saying that, hey, we start off with maybe 0 slope, so 0 velocity. We increase to negative slope, which is going to be negative velocity. We're going towards the middle. We're starting off positive, going towards the middle. At the end, we are sloping back to 0, and then we're turning around. So we're going to get positive velocity there. So the slope is a big tell of the velocity. Now, what happens here is that the slope is changing, right? Well, if the slope is velocity, that means that we have some kind of change of velocity over some kind of change in time. And again, the calculus would be a dv over a dt, some small change in velocity over some small change in time. And that's going to say we got some kind of acceleration to talk about too. That acceleration is going to be changing. So not only is the position changing, the velocity is changing, the acceleration is changing. All right, that's just the basics of what's going on here. This is a mass on a spring, so let's work some equations that have masses and springs. So we know that the force of a spring is equal to negative k delta x. All right, and so based on how far this is displaced, this is going to have more force. Well, the other thing we can write down is that force is equal to ma. Not sure if we're going to use it or not, but we might. What else can we write down here? We've got the, we can write down period. We know the period of a spring is 2 pi, the square root of m over k. All right, m over k, because the mass is actually, the spring's actually trying to move that mass itself. So the more mass you got, the longer it's going to take to move back and forth. Double checking, we know the mass, that's 5 kilograms. We don't know k, but we could find the period, because the period is the time for it to repeat itself. So it looks like the period here that I drew was 1 second, or I just labeled that. So if I know that the period t is 1 full second, then I can actually, I have all I need to find k. So let's go ahead and do that. So period is 1 second. That's equal to 2 pi. The square root of m over k. M is going to be 5 for the kilograms, and k is going to be a value that I can find. Tell you what, if I want k, I'm going to square everything. 1 squared is still 1. 2 squared is going to be 4. Pi squared is going to be pi squared. Square is going to take off the square root. That's going to give me a 5. Divided by k, I'm going to move it over here, change that 1 to a k. And k is going to be all this stuff. So what is that exactly? We've got 5 times 4, it's 20. We're going to multiply that by pi, and we're going to square it. That's going to be 197.4. So 197.4, boom, newtons per meter. We just found the k value. Okay, well, what else can we do? If we know the k value and we know the displacement, let's say maximum displacement is 0.5, we can find the maximum force of the spring, or better yet, we can find the acceleration that this spring provides at maximum over here or over there. And so let's go ahead and find that. So the acceleration is going to be negative k delta x divided by m. And we're going to check out the maximum acceleration here. And if we do that, we're going to talk about the maximum displacement x. And so I'm just going to call it either 0.5 or negative 0.5. I'm not really going to worry about that negative in the equation because I'm looking for the maximum acceleration magnitude of it. So our maximum magnitude of the acceleration is going to be our k constant value, 197.4, times my maximum 0.5 displacement divided by the 5 that we got for the mass itself. 0.5 divided by 5 is going to be that 0.1, right? 0.01. 0.5 divided by 5 is going to be 0.1. Yeah, there you go. And then 0.1 times 197.4 is going to move that over a decimal. And so we should have 19.74. Let's just double check though, make sure my calculation is right. 197.4 times 0.5 divided by 5. And we got 19.74. So we now have the maximum acceleration is 19.74 meters per second per second. That's plus or minus because we are on either the top or the bottom up here or down there. All right, we got the position, we got acceleration. Let's see if we can hit that velocity then. We know the velocity on the sides here are at a minimum, which we're turning around, right? So the velocity here, the velocity there, we're turning around, that's 0. The velocity in the middle, though, it's kind of a question mark. How do you get the velocity in the middle? Remember, all we're doing is we're working with this graph, just this graph. We have no other information than this graph of position versus time. And it's kind of weird that we can get all this stuff, but we can. So let's talk about the velocity. Let's see, the velocity comes from what? Well, it comes from the spring pulling it back towards the center, So if we're talking that this spring is moving, let's talk energy, all right? On the sides, this spring that's going back and forth, back and forth, back and forth, back and forth, it's going to have potential energy to kinetic energy to potential energy back to kinetic energy back in the middle. Anywhere in between the middle and the side is going to be a combination of both. I don't want to talk about the combination of both, but I do want to talk about the extreme cases, which are here, here, and then right in the middle. We know on the sides it's turning around. In the middle, that's kind of the big question. What is our maximum velocity? So the maximum velocity is kind of a question mark that I want to answer. And the way we can look at that is energy. So on the sides, we know that we have mechanical energy. It's all going to be our spring or elastic potential energy on the sides. And in the middle, it's going to turn all to the kinetic energy. All right, translational kinetic energy is moving back and forth, back and forth, back and forth. The spring potential energy is going to be 1/2 K delta X squared. And we're looking at the maximum amount that we have, so that's going to be the maximum X. And good thing we found out K earlier, that's pretty good. So we got the maximum X, we got K. Our kinetic energy is going to be 1/2 mv squared. And we know the mass, so we actually have everything we need in this equation. So if we just do a little bit of algebra, we'll take the halves away because both sides have halves. We can just multiply both sides by 2. For the K value, we just found it to be 197.4, and the maximum X value is about 0.5. Doesn't matter if we use negative or positive here because we got a square on it right there. And then we're going to equal this to the M on the other side, that's 5, and we got a V squared there. So really, we're going to divide this 197.4 times 0.5 squared, divide all that by 5, and then we're going to square root that thing. And so that's going to be my velocity, maximum velocity. That's going to be my maximum velocity in the middle as we are traversing back and forth, back and forth, back and forth. It's either going to be positive or negative, but that depends on which way we're going. So let's see, 197.4 times 0.5 squared, 2.5, divide that all by 5, and I'm going to square root that. You see how I'm kind of doing everything in separate steps in my calculator? That's the easiest way to avoid having that PEMDAS, you know, the order of operations errors that you might have. So again, 3.14. Oh, that's interesting. For my maximum velocity, 3.14 meters per second. And that's going to be a plus or minus as well. So we have all this information. We found, we could find the maximum potential energy and maximum kinetic energy. I don't care about that right now. But we have all this information to make these other graphs that I was kind of planning on making in the first place. So let's go ahead and look at the velocity graph. And so the question here is, if we have a velocity versus time graph, let me space that out the same way that I spaced out the other one. Every 2 would be appropriate. And the graph paper is kind of weird. I don't know why I did that. But this is going to be 0.5 seconds. That's going to be 1 second. That's going to be 1.5 seconds. And then somewhere over here is going to be 2 seconds. I might run out of that. But for your velocity, what I need to look at is, you know, how does this match up with the position graph? And what we said was, you know, in the beginning, this thing is going to be turning around, or it's going to be starting off. So we know the velocity in the beginning is 0. Okay, so I'll put a big dot there. And every time we have a peak or a trough, we're going to see that velocity being 0 again because we're turning around. So at 0.5 seconds, we should see some kind of velocity that is negative. How should I do that? Let's put it right here. I'm not sure. Oh, we know the value, don't we? The maximum velocity is going to be 3.14 meters per second. So I'll just put it around here. Let's call each of these 3. 1, 2, 3.14, about there. So 0.5, we have some kind of velocity, or actually we have 0 velocity. That's what I said, 0 velocity. At 1 second, we have 0 velocity again. At 1.5 seconds, we have 0 velocity again. So, and in 2 seconds, we have 0 velocity, which is somewhere over here. I don't know. I'm not sure where it is. Now the question is, what is the velocity like at this midway point? And as we said in the first place, that velocity, found a ruler, is the slope of this graph, right? So if we look and do a little tangent line action, that tangent line should be the velocity, and that velocity should be negative. So at this point, we should have a negative velocity. That should be my negative point right there. And then here at the next one over, we should have a positive velocity. So that's going to be 3.14 the other way. It's going to be somewhere up here. And so the way that this graph is going to turn out, it's going to be repetitive. And it's going to be looking something like this, where we start off and we are going down like so, coming up. Come on, pen. Coming down like so. Coming up. And coming down like so to somewhere over here. I'm not sure where. It's getting kind of messy. And if you watch the other video, this is turning into kind of the same drawing, but now we actually have numbers And we can apply a negative 3.14 here meters per second. And this will be a positive 3.14 meters per second up there. So this thing starts off with no velocity, goes to negative 3.14 because it's going backwards, and then it goes no velocity again. It has to turn around, goes positive 3.14, and it's going back and forth and back and forth, back and forth, back and forth on a spring. Last graph that we can do is going to be a acceleration graph versus time. I'm going to space this out the same way. Let's call this 0.5 seconds. And this is going to be, again, 1 second. And that's your 1.5 seconds. And this is at the end of your, well, actually, wait, did I do that wrong? Whoop, right there, missed it. 1.5, and then right there, there's going to be your 2, somewhere down here. Okay, so this acceleration, again, what's the question that we need to answer with the acceleration? What values does it go to and come from? So the acceleration over here, the maximum acceleration is either 19.74 or negative 19.74, depending upon where we are. The acceleration, as we said before, was the slope of the velocity graph. And so if you notice where our slope is 0 is here, here, there, and there. Okay, so at those points, we should have 0 acceleration. And somewhere over right there. So at those points, we should have 0 acceleration for our object. Let's correspond that back to the beginning. There, 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 and there. And that should make like total sense because this thing is a mass on a spring. It's moving back and forth, back and forth, back and forth. It wants to be right in the middle. That's where the force is 0. And if force is 0, the acceleration is 0. And that's exactly what this is talking about. All right. Now we need to figure out, well, we know the maximum and minimum values of our acceleration. Now we need to figure out where those are. So again, the slope of your velocity line is going to be your acceleration. So here, in the very beginning, we've got this negative slope here. And so that negative slope is going to be a value down here. Let's just make it right there. And then when we have a positive slope, that's our most positive maximum slope right there. And we're going to have that positive acceleration, 1, 2, 3, 4, just to match it on the other side. And so with this matching up each and every time, that should be okay. And it works out. And then something down here. And so now what we have is this acceleration that starts off negative at a value of negative 19.74, and it ends up positive 19.74, and it's meters per second, or meters per second squared, right? And so we start down here, we go up, and we go down again, and we go up, and we go down again, and we turn around. So we are looking at this acceleration that again starts off negative, goes positive. It has to go through 0 to get to positive, right? And so that tells us, hey, at some point there is no acceleration, there is no force, because forces cause acceleration. And does this make any sense? At the beginning, our acceleration is negative. Okay? At the beginning, our position is positive. But then our position becomes 0 and then negative. So we're being pulled back towards the 0 value of position. Well, to do that, we needed to move. And well, you got to get going. We start off at rest, and to get going, you got to have an acceleration in the negative direction. So all three of these do match up. And we got all this from just this graph of position versus time. And so it's using basic physics. All we did was use basic physics here, and we got all this stuff, and the math kind of came out of it. All right. If you wanted to, you can use some sine and cosine formulas to make equations of motion for the position, velocity, and acceleration. But I'm not going to do that. That's more of an AP Physics C level. If you want to do that, go ahead. But I'm going to stop the video here. All right.